highly thank you, Christophe, for accepting to present your analysis and all the work you have done on the topic of intelligence, artificial intelligence, internal modeling, which is a very highly up-to-date concept and work, and very complex. So let me just say a few words. First, that artificial intelligence is becoming established in the landscape, and SCOR is determined to take full advantage of its use. But to what extent artificial intelligence can really be used and how it's used to use it well remain key questions. Naturally, when we talk about artificial intelligence, we immediately turn to quantitative modeling. To what extent can it enable new generations of models? Or at the very least, to what extent can it improve existing models? One of the big challenges that models face when they seek to use artificial intelligence is the one of intelligibility. How to distinguish spurious correlations from relevant correlations inside the final results of artificial intelligence. Econometrics has developed relatively sophisticated techniques which unfortunately are not immediately transposable to artificial intelligence modeling. In the meantime, alternative solution consists of systematically testing artificial intelligence models to more traditional and classical models. This is what Professor Hurlin is proposing to us, i.e., comparing artificial intelligence models for banking to traditional internal models for calculating banks' capital requirements. In the absence of studies on insurance and reinsurance, I thought, it will be very interesting for SCOR's quantitative teams to investigate the case of the banks, to draw lessons in terms of data and artificial intelligence for insurance and reinsurance. I would like to thank Professor Christophe Hurlin for agreeing to share with us the work, the very valuable and exceptional work he has carried out on this subject, as well as the conclusions he draws from it. I think that these conclusions will be extremely useful to us within the framework of SCOR data approach, particularly in relation to the modeling of our activity and its validation. Christophe Hurlin is Professor of Economics at the University of Orléans, Director of the Laboratoire d'économie d'Orléans, and member of the Scientific Council of France's Financial Supervisory Authority, the ACPR, Autorité de Contrôle Prudentiel. He has also been consultant to the World Bank. This was to be mentioned. To the participants, please don't ask questions during the presentation, except in case of misunderstanding. Questions will be gathered after the presentation. Dear Christophe, thank you so much. And now the floor is yours. You have in between 30 to 60 minutes for you, up to you to choose how much time you need. Thank you so much.
Thank you, Philippe. Good afternoon, everyone. First of all, I would like to thank Philippe Trainard for this invitation to present my research at this SCOR webinar. I think that I will skip my presentation. It was done by Philippe, but just to mention that my research areas are econometrics, financial risk management, and credit risk. And you can visit my Google Scholar page or my personal web page for more details about my research. So I'm here today to present with you a report that we recently published with my colleague Christophe Hurlin from HEC Paris. sorry, just a minute, up here, up, yes, from HEC Paris for the Institut Louis Bachelier. So in this report, we propose a theoretical and practical reflection based on the academic literature on the use of machine learning method in the specific context of internal rating-based IRB approach to banks' capital requirements. So this is not a topic in insurance. I'm sorry, but I'm not a specialist of insurance. However, I believe that the discussions we have within the banking industry regarding the use of ML for regulatory capital models may offer valuable insights for insurance industry with respect to regulatory provisioning and economic capital. So we decided to work on this subject after the publication by the EBA of a discussion paper on the use of machine learning for IRB models in November 2021. And the objective of the regulator was to lay the foundation for discussion on the subject with banks and to study with them the compliance of the most sophisticated machine learning method with capital requirements regulations, so the famous CRR. And following this discussion with the industry, the EBA has recently published a few months ago a follow-up report which summarizes the discussion, and we'll discuss about these conclusions today. So when the EBA published its discussion paper in 2021, it sparked a lot of debate in the financial industry. Okay, some commentators argued that the EBA had opened the door to machine learning in regulatory applications. Others, such as Professor Hurlin from Oxford, were more skeptical and just said no way, no to the machine learning in the IRB context because these models are too opaque, too complex for such a high-risk application. But in general, most commentators were more positive about the use of machine learning for IRB models. They argue that ML models can be used to improve the accuracy of risk models, to identify new risks that are not captured by a standard logistic regression, for instance, and to allow banks to reduce their regulatory capital while ensuring their financial stability. Whatever we think about this perspective, there are two paradoxes. The first is the fact that contrary to what has been written, the EBA did not open the door to ML in 2021 because the door was already wide open. So in the current regulatory framework, nothing prevents banks to use ML algorithm to estimate credit risk parameters, either for the PD, for the LGD, or the credit conversion factor, CCF. For instance, there is no article in the CRR that prescribes the use of a XGBoost or a random forest method for modeling PDs. However, in practice, only a handful of banks currently use ML in the IRB context. And when they do, these techniques are often confined to the pre-processing of the data or the construction of challenger models. The second paradox is the fact that the EBA discussion paper was published less than a month after the publication of the CRR3, CRD6 banking package. So the so-called Basel IV or Basel 3.5 agreement. And this package was precisely designed to reduce the variability of capital requirements among IRB banks, and for that, to reduce the degree of freedom given to modelers in the IRB context, for instance, by introducing input floors, capital floors, by removing the AMA approach for operational risk, etc. So we have two seemingly contradictory signals from the regulator. They want to reduce the variability of capital requirements among IRB banks, and at the same time, they launched a discussion about the most flexible models that we could imagine for risk parameters. So on the one hand, more model and less model on the other hand. So in the report, we discuss this paradox, and we refer to the issue of banking competition and market protection, particularly with regard to the big techs. But let me focus here on the first paradox. To illustrate my point, let me consider two surveys conducted by the Institute of International Finance on the use of ML in the credit risk industry in 2019 and 2022 among 60 banks and 43 international banks, respectively. If we ask, do you apply any machine learning techniques in your credit risk-related analysis? Most of the banks answer that they use ML in production. So we have 52 banks today that use, in this survey, that use ML in production. And 25% of the banks use for pilot projects. Notice that in the survey, also Eurozone and US banks use ML methods in production today. So ML is largely used by industry for all types of portfolio. The highest adoption rate is observed for retail lending, but the machine learning is also used for other type of portfolio. But when we distinguish the use of machine learning, we observe that these techniques are widely used for credit scoring, credit decisioning, monitoring, restructuring, and recovery. But on the contrary, we observe that ML techniques are rarely used in the context of regulatory capital. In 2019, only 15% of banks report using or planning to use ML for regulatory capital. And even worse, the use of ML declined between 2018 to 2019. More generally, we observe a lack of popularity of machine learning models in the regulatory framework, for instance, for stress testing or provisioning, so IFRS 9, for instance. So, given this context, I will focus my discussion on 2 points. My first question is, what can we expect from machine learning in the IRB context? And here, we will discuss the potential gap that could occur between the accuracy gains, for instance, in terms of R-squared or IUC and so on, and the economic gains, for instance, in terms of capital requirement or risk-weighted asset. And we'll try to explain such a low adoption equilibrium amongst banks. And the second point concerns the challenge of interpretability or explainability. When banks are asked about the main challenges of machine learning, they first mention the lack of interpretability of this model. So the issue is based on the belief that there is a trade-off between performance, statistical performance or economic performance, and interpretability. This is the idea that the most performant models are necessarily black box models. And in this report, we argue that it is not necessarily the case. And for us, there is no arbitrage between performance and interpretability. And we advocate for the use of a natively interpretable machine learning in the IRB context, and I will explain this concept. So first, let me define what is machine learning in a regulatory perspective and discuss the potential uses of this method. So according to the standard definition of machine learning, it covers a wide range of algorithms, from the simplest ones, such as logistic regression or classification tree, to the most sophisticated ones, deep learning and so on. However, in this discussion paper, the EBA focuses on the most complex models, which are also the most difficult to understand and to use for regulatory capital purposes, with a high number of parameters, etc. So in other words, machine learning in this context corresponds to black box models, so that are not natively interpretable models. Okay. And now, in the IRB context, machine learning can be used for the modeling of PD, LGD, or CCF at every stage of the modeling process. So it could be used, for instance, for data preparation and feature engineering. So for instance, for the imputation of missing value, for the discretization of features, for dimension reduction, clustering, whatever. It could be used for risk differentiation. In this case, ML model is used to produce a continuous score or to build the rating grades that will be used by the banks to compute the PD in the next step. It could also be used for risk quantification. Okay. For instance, when you want to increase or decrease the PD for a given rating grade using unstructured data, for instance, financial reports by using NLP, so natural language processing. Finally, it could be used for model validation, especially for the creation of challenger models. And this is the most frequent use of machine learning in this context. Clearly, the level of attention devoted to ML should depend on the type of its application on the IRB context. And the most significant issues arise when ML is employed as a core model used for the risk differentiation. In our report, we summarize the main answers from banks and banking professional association to the EBA. I don't have time to present all these responses, but it is worth focusing on some of them to get a sense of current practices. So in the EBA document, the first question was, do you currently use or plan to use machine learning models in the context of IRB in your institution, and for the estimation of which parameters does your institution currently use or plan to use model PD, LGD, CCF? And in this part, the French Banking Federation, for instance, confirms that currently their members do not use machine learning in the risk differentiation phase of PD models. And their reasons primarily involve regulatory uncertainty about the acceptability of this model, as well as difficulties in interpreting these techniques. Well, the second question was, can you specify for which specific purpose this model are used or planned to be used? Data preparation, risk differentiation, risk quantification, validation. And for instance, the French Banking Federation indicates that ML are used mainly for variable selection and the construction of challenger models. The third question was, please specify the type of ML models and algorithm you currently use or plan to use in the IRB context. And it's difficult to establish a list of the algorithm used by banks, but the banks mainly mention two types of algorithm. The first is a random forest, and the second is gradient boosting tree techniques. Okay. Finally, the EBA also mentions the potential use of unstructured data, mainly text data, for instance, financial reports in the IRB context. And what do we mean by new data? So in 2019, with my colleague Christophe Hurlin, we published a paper about the use of this new data for credit scoring, but we didn't consider the specific IRB context. And we introduced, for instance, the concept of data diversity, which cover digital footprint data, social networks, textual data, etc. And in this paper, we discuss the consequences of using this new data for the accuracy of credit scoring models by using or not machine learning in complement, and the organization of credit industry with the emergence of new players, financial inclusion, and etc. I think that it may be a game changer for the future of credit industry, but this is beyond the scope of my presentation today. Why? Because no bank currently uses this new data in the IRB context, mainly for governance reasons. Okay. So, what can we expect from machine learning in the IRB context without this new data? So before answering, let me clarify the background. So we focus on the use of ML method used as a core model for risk differentiation. We consider a constant information set, that is, without introducing new data in the IRB context. And we consider ML models that are not interpretable as defined by the EBA. And in this framework, we have two questions. The first is, what gains can we expect from ML in terms of predictive performance or predictive accuracy and productivity? And the second question is, what gains can we expect from ML in terms of regulatory capital? So when you ask to banks what are the expected benefits from ML in credit risk modeling, the top three answers are the improvement in the accuracy of risk parameter estimates, the identification of new risk segments, and the productivity gains. Okay, let me focus on the first point, that is the improvement in the accuracy. So the use of machine learning in credit scoring is a long-standing practice. In the academic literature, ML was first applied to credit risk modeling in the 80s. For instance, the CART algorithm for the well-known classification tree was published by Brayman and his co-authors in 1984. And the CART algorithm was used for a credit scoring application less than a year after by Makovsky in 1985. The same is true for neural networks and so on. So most of the ML methods currently used by banks were developed between the mid-80s and the early 2000s. For instance, the bagging method was published in 1986 and the random forest in 2001. So the only exception is the XGBoost, which is more recent. However, the boosting technique hasn't been known since 1987. So my point is that we have insight on the performance of the machine learning methods in the specific domain of credit scoring. How can we summarize the result of the huge academic literature devoted to ML in credit scoring? First result, there is no significant accuracy gain with individual ML classifiers. So as soon as 2003, my colleague Bart Bassens and his co-authors show that, for instance, support vector machine and neural networks offer very good predictive performance in credit scoring. But for most of credit scoring cases, databases, the difference between the IUC of the best ML method and that of a simple logistic regression are generally less than 2%. So how to explain this result? This result is due to the fact that there is few non-linearities in the data, in the credit scoring data. So to illustrate this idea, let's take a look at the summary plot of the SHAP values for two random forests, one used for a credit scoring model and one used for a breast cancer detection model. So for people who don't know what is SHAP, values summarize the influence of a model feature on the predicted outcome, okay? So if the SHAP is positive, it means that the feature tends to push the probability of the event above the mean probability, okay? So in this graph, each point in the plot represents an individual or a credit, and the color indicates the value of the feature. Okay, so red point indicate high value and blue point indicate low value. So in the credit scoring model, we observe that the blue points and the red points are clustered each other. This means that the influence of each feature is relatively linear in this model. For instance, If you consider the funding amount, a high funding amount generally increases the probability of default. Okay, it's here. In the breast cancer model, the points are more spread out. Why? Because this is the influence. This is evidence that the influence of each feature is complex and nonlinear due to interaction effects and so on. For instance, if you consider the age, okay, the age feature may have a positive or negative effect on the risk, depending on other factors such as smoking status, number of pregnancies, genetic factors, whatever. So the point is, in credit scoring, we have less nonlinearities than in many other application field of machine learning. And this explains why usual ML classifiers, support vector matching, decision tree, whatever, do not outperform standard parametric approaches in credit scoring. Okay? This is not true. It's not a generality. It's not true in other research field, but it's specific in credit to the credit scoring dataset. The second result is that, on the contrary, there are significant accuracy gains when we consider ensemble methods. So there are different ensemble methods. The most well-known are bagging, boosting, and stacking. So the intuition is the fact that combining different elementary classification models reduces the forecast variance. Okay, it is, for instance, the idea of the bagging. Okay, this is an old idea in econometrics. This is the idea of a combination of models that leads to more robust forecast. Okay, so in a benchmark studies, Lessman and co-author consider 41 algorithms, 12 assessment criteria, and 8 credit databases, and their conclusion is that random forest, which is a bagging technique, and XGBoost, which is a boosting techniques, dominate individual classifiers. So the logistic regression tree, the classification decision tree, the artificial neural networks, and whatever, in terms of IUC, recall, precision, whatever. And the gains are significant. This explains why these two algorithms are the most often used by banks today, as we discussed before. Okay. Now, the third result is that the accuracy gains from methodological refinements of ML algorithm tend to plateau. For instance, using heterogeneous ensemble methods instead of homogeneous ones, rotation forest instead of random forest, deep learning techniques, etc., does not significantly improve the accuracy of the PD estimates compared to the usual ensemble methods that I mentioned before. For instance, in this figure, the author from Bank of Spain report the gains of IUC obtained with ML techniques with respect to the standard logistic regression model in the academic, some academic publication according to the model complexity. Okay, and the conclusion is clear. There is no hope of finding a magic model that would boost the performance of your scoring model far beyond that of ensemble methods. Okay, so ensemble methods are here. And there is no hope to find a model that will increase your IC from 0.8 to 0.9999. Okay, and this is confirmed, for instance, by a recent paper specifically devoted to the use of deep learning methods for credit scoring. And the title of the paper is explicit, do or don't, and the conclusion is also explicit, is don't. The authors show, for instance, that deep belief networks don't perform better than XGBoost, but are considerably more computationally expensive to build. Okay, I can give many other examples. The fact is that many authors consider today that research on developing high-performing credit scoring model as more or less stale. Another time, this is not a general result. I don't say that, okay, there is no gain with methodological refinement of ML in every field. Okay, it is specific to the credit scoring industry. So to sum up, the academic literature clearly shows that banks could obtain significant accuracy gains with ensemble method compared to the standard logistic regression approach for the PD estimation. So I don't have the time to present the result for the LGD, but we discussed this point in the report, and it is approximately the same. So the question is now why banks do not use these techniques for their PD internal models in the IRB context. And my point is that banks will only adopt machine learning for the IRB model if they have an economic advantage. So if it's permitted to reduce their capital requirement, to be clear. Okay. And this raises the issue of the concordance, of the divergence between the accuracy gains in terms of IUC and the economic gains in terms of risk-weighted assets. And the problem is that higher accuracy in the estimation of risk parameters does not necessarily imply lower RWA or regulatory capital for at least two reasons. First, there is no evidence that the predictive gains associated, for instance, with a random forest or a Gaussian boosting techniques are due to an overestimation of default risk by traditional logistic approach. I know that, okay, there is an accuracy gain, but I never said that, okay, the logistic regression tends to overestimate or underestimate the probability of default. Second, even if machine learning method allow to reduce the regulatory capital, these models still must be validated by the internal validation team and most importantly by the supervisor. And so they must pass the standard validation test procedures. And a recent academic study published in Journal Banking Finance by Fraisse and Laporte in 2022 answer to these questions. And just a remark, both authors worked at the ACPR, so they perfectly know the IRB model and the supervision process. Okay, so for the analysis, the author used granular data on 6 corporate credit portfolios from large French banking groups, and their data cover 5 million of observation, representing 80% of the credits over the periods. And they consider historical quarterly data over 5-year origin to build the models. And then they validate the model on the observation from 2015. Okay, so their methodology is very simple and convincing. Okay, it consists in reproducing a bank's IRB methodology. So in the first step, they built a continuous risk score as a function of risk factors using either a logistic regression or a ML algorithm. So they consider 4 ML methods, namely a random forest, XGBoost, ridge regression, and artificial neural network. So the machine learning is only involved in this first stage. Then, in a second step, they built a discrete risk scale from the continuous risk score. To do this, they group the firm into rating grades according to constraints on risk score homogeneity within a grade and risk score heterogeneity between grades using a top-down segmentation algorithm based on Z-test, but I don't have to detail. Their goal is to build risk classes that pass regulatory tests on the training dataset. Okay. And in the last step, a PD is assigned to each risk class based on a 1-year history of observed defaults, and capital requirements are calculated using the standard Basel formula. Then, the model are validated on the test sample using 3 criteria. So the accuracy, measured by the IUC, so area under the ROC curve, the gain in capital regulatory capital measured by the RWA densities. It is a ratio of risk-weighted asset to the total exposure, and the risk differentiation index to check if the model will pass or not the validation test. Okay. So their conclusion reveal huge differences in the ability of ML models to pass validation tests and reduce capital requirements. So as concerns the predictive performance, the results are in line with the academic literature. Okay, so the random forest outperform the traditional parametric model in predicting corporate default. Okay, but random forests are subject to overfitting. Even the hyperparameters have been calibrated by cross-validation and so on. Due to this overfitting, the random forests IRB model fails validation test in the test sample. Okay. The XGBoost model also improve the accuracy of the PD estimation, but it leads to an increase of the risk-rated asset compared not only to the logistic model, but also to the standardized approach, that namely the approach without any internal models, okay, based on our external ratings. And on the contrary, neural networks and traditional logistic regression pass compliance tests, and neural networks provide capital gains compared to logistic regression. So to conclude, why the accuracy gains of machine learning are certain, the economic gains are not. And there is a problem because the most efficient models in terms of accuracy improvement are not those that offer the best economic performance. Okay, to illustrate my point, let's consider the chart that compares the IUC around the row curve calculated with ML models and that calculated using a traditional logistic regression. Okay, so when this difference is positive, it means that the ML model offers an accuracy gains. When it's negative, there is a loss. Okay, so we compare gradient boosting, ridge, neural networks, and random forest. Each box represents the minimum, the first quartile, the median, and so on for the population of the 6 banks in the study. And the results confirm the finding of the academic literature, the fact that the best IUC gains are obtained with, for instance, here, random forest, because you have a gains for all the banks. Okay, and on average, you have a gains of 4%. Now, this chart shows the difference between the weighted risk densities calculated using the ML models and that calculating the logistic regression. When the difference is positive, it means that the use of a ML model increases the capital requirement. And this is, for instance, the case of the gradient boosting. We observe an increase of the risk-weighted asset compared to the logistic regression, whereas the model was more performant than logistic regression in terms of IUC. Okay, we have an increase in the IUC, but you have also an increase of the risk-weighted asset. And the contrary, random forest model allows a large decrease of the risk-weighted asset for some banks up to 40%. But this is due to overfitting, and even the hyperparameters have been fine-tuned by cross-validation. Okay, and for this reason, the random forest fails to pass the validation test. Okay, we have also similar result for LGD modeling. For instance, in 2018, with 2 colleagues, we published a paper in which we evaluate the various loss functions defined in terms of regulatory capital for LGD model. So loss given default. We compare the forecast of different loss given default models, including various ML models. And we show that ranking of the model based on the capital loss function differ from those obtained based on standard statistical criteria. Okay, if I rank the model according to the MSE, so mean square error, and if I rank the model according to a capital loss function, I don't have the same ranking. And this confirms that there may be a discrepancy between the gains in terms of statistical accuracy and the gains in terms of capital requirement. So my point is that this discrepancy may explain the low adoption equilibrium of machine learning method observed among banks, even we know that the ensemble methods allow for accuracy gains in the PD or LGD estimation. Okay, so the second main issue with the use of ML in the IRB context is the challenge of interpretability, explainability. When we ask to banks what are the main challenges they face when implementing ML in credit risk modeling, they first cite the model interpretability and explainability, both for internal control and external authority. So the issue of model interpretability of explainability is a central concern in all high-risk application of ML and AI. So these problems arise because the ML models generally used by banks are ensemble methods. And for this model, it is impossible to understand the factors that contribute to the prediction. So we have some black box model. In the IRB context, it is not feasible to entrust the determination of a bank's regulatory capital to a black box model, okay? Because the supervisors, the internal validation services must be able to understand and to explain how the risk parameter used for calculating capital requirements reflects the level of risk taken. So we need to use ML interpretability method. So in terms of terminology, first, we have to distinguish between interpretability and explainability. Or interpretability refers to an overall understanding of the model, while the explainability refers to a local understanding of individual decision made by the model. Okay, the fact that the credit was denied for Christophe Hurlin, for instance. So we have also to distinguish between intrinsic interpretability, so the models that are interpretable because of their simple structure, for instance, a decision tree, and the post-hoc interpretability refers to the implication of interpretation methods that are applied after a black box model has been trained. And so when we try to explain after the model after it has been trained. Okay. So indeed, when models derived from ML algorithms are not interpretable a priori, the usual approach involves implementing a method to make them interpretable ex post. And this method are said to be model agnostic, as we can use to interpret the result of any ML model. And the general idea of this method is to perform reverse engineering based on inputs, so the feature, and output, so the prediction of the model, such as to reveal the algorithm decision. So if a bank uses ML model in the IRB context, there are a new step in the model validation process that consists in using ML interpretability method. Okay, so you have the data, you have your model, and then you have an interpretability method. Okay. Alors, there is a wide range of interpretability method for ML model. This is because there is no single perfect explanation of a model, and the best explanation depends on the stakeholder, okay, who is asking for the to understand the model. Okay, we can broadly categorize interpretability methods in two types: global and local. So global methods are related to the interpretability, and local methods are related to explainability. Some examples of global interpretability method include the PDP, so partial dependent plots, the accumulated located effect, feature importance, surrogate model, etc. Some example of local interpretability method include the Shapley value, okay, SHAP with SHAP method, also LIME, so local interpretable model agnostic explanation. So this is an example and output of the SHAP value, okay. So Most of these methods are now taught in many master programs, for instance, in our master at Orléans, and they are now widely known. And we observe that in practice in banks, the interpreted methods generally used by banks are PDP, feature importance, SHAP, and LIME. Okay, but what's important to note is that each of these methods provides only a partial understanding of a model, and their usefulness can vary considerably from case to case. Okay, the approach of using a black box model for risk differentiation and then implementing global or local interpretive method is highly debated. For instance, Professor Cynthia Rudin from Duke University calls for a complete cessation of the use of black box model for high-risk application. Even this model are accompanied by interpretable ML methods. And the first reason is that these methods provide explanations that are not faithful to the original model. And by design, they just provide an approximation of the decision rule of the model. Otherwise, the model would be interpretable. Okay. A second reason is that sometimes the explanation provided by this method don't make sense. And the third reason is that the explanation provided by different interpretability methods for the same model are sometimes inconsistent. For instance, you use a Shapley value and a LIME, and you don't have the same story about the global how the model works. Okay. And this is on this point. This is an interesting article by Krishna on this subject, which I recommend to you. Finally, there are more specific arguments in the context of credit risk. For instance, a recent article of Chen et al. Highlights the instability of interpretation provided by LIME and SHAP in the case of low default portfolio. Okay, we know that the problem of imbalanced data is well known. We know that it both influences the learning capacity of the model and invalidates some evaluation criteria. But now we have another problem. The imbalanced data have also an impact on the reliability of the interpretability method. So why do we continue to use black box model with post-hoc interpretability method, for instance, SHAP? And why does the EBA mentions this solution in the IRB context? And the main reason is that there is a widespread belief that complex black box model provide more accurate risk parameter estimates than less complex model. And because this overperformance, it is rational for banks to accept the use of opaque model and then to apply a Shapley value despite their limitations. To be clear, if JBoost outperforms the other model in terms of IUC, it's rational for me to use them and then to compute the ex-post Shapley value to understand how the model works. Okay, and this belief is based on the idea of a trade-off between performance and interpretability. However, this alleged trade-off between performance and interpretability is increasingly being challenged in the academic literature. So in a recent paper, Semenova and co-author, including Cynthia Rudin, introduced the concept of Rashomon set, which is defined as a set of predictive models that deliver a similar accuracy to the optimal black box model. Okay, the idea is intuitive. Okay, for many applications, there are several different models, for instance, a random forest, XGBoost, whatever, with different functional form and prediction, which perform almost as well as the best model. And they argue that in most of cases, the Rashomon set is probably sufficiently large to include interpretable models. And so, if this theory is verified, for each classification problem and regression problem, a model exists that are both accurate and interpretable. So there is no need to use Shapley value, LIME, PTP, etc. There is no trade-off between performance and interpretability. Okay, but in practice, we still need to find some credit risk models that are both efficient and natively interpretable. Several recent studies have shown that is achievable in practice. And in the report, we cite many methods. For instance, with my colleague, we recently published a paper in which we propose a penalized logistic tree regression, so PLTR method. Okay, formally the idea is very simple. We extract binary rules from various shop depth decision trees built with the original feature. Here we consider shallow trees with only 2 features. Given these rules, we built binary variables that are then introduced in the simple logistic regression model, which is estimated by an adaptive lasso penalized regression. Okay. The idea is to automatically select the most important predictors. So at the end, whatever the details, at the end, we have a standard logistic regression with binary explicative variables that allows us to take into account the non-linearities and the cross and the interaction effect. So the credit scoring model we propose is natively interpretable, and because we can compute the order ratios, marginal effect, etc. And the question is to know if it works. And it works. This pre-processing improves the predictive performance of the logistic regression by capturing threshold effect and interaction effect. And in the paper, we use 4 the credit data set, and we show that the PLTR model can predict default as well as random forest, for instance. Okay. So in terms of IUC, PGI, PCC, etc. PGI is partial gene index, PCC percentage of correctly classified cases, cases chromograph. So we don't say that our model is better, okay? But it gives approximatively the same accuracies as a random forest. Thus, we have a model which is both accurate compared to a black box reference model and interpretable. This is just an example. In the report, we cite many other methods in the same vein, but I don't have time to develop here. There are many possibilities to find a model which is both performant, accurate, and interpretable. More generally, I think that the myth of the trade-off between accuracy and interpretability is ingrained in the mind of credit scoring professionals and academics. However, we guess that this new approach of natively interpretable machine learning is likely to develop within banks in the coming years, especially in the IRB context. And we cite, for instance, the research currently being conducted by Wells Fargo, especially by Agus Sujanto, the head of corporate model risk. And his team has recently, for instance, developed a Python toolbox for interpretable machine learning, which is PyML. And this toolbox includes many interpretable ML methods such as explainable boosting matching, EBM, which are similar to generalizative model, but automatically detect and include pairwise interaction terms, or GAM-MAGNET, which are GAM models with structure interaction, etc. So Wells Fargo team is very active in promoting this natively interpretable ML method. So to conclude, ML methods generate more accurate estimate of race parameter, PD, LGD, CCF, and than those provided by standard parametric approaches. It is true. These gains tend to plateau with increasing model complexity. But some ML models, generally based on ensemble methods, could offer a significant improvement in the accuracy. But at the same time, some models could offer a significant reduction in regulatory capital while guaranteeing that the usual validation terms are passed, but they are not necessarily the best model in terms of standard statistical criteria assessment. So the question is how to justify the use of ML IRB model, because maybe I can have you can have a stable low adoption equilibrium. Okay, why? Because if a bank uses an ML model and achieves a significant reduction in its RWA, there will be a suspicion of regulatory arbitrage. Okay, for instance, on the choice of hyperparameters, the choice of the algorithm, and sometimes there is no possibility to justify to the supervisors the use of this model with standard statistical criteria because my model is not the best model in terms of IUC. On the contrary, if the bank does not achieve a significant reduction in its risk-weighted asset, it has no incentives to change its standard model based on the logistic regression for an ML method. And this could explain the low adoption equilibrium that we observe in practice. Now, the last point is the change of model interpretability. And we think that there is no arbitrage between performance and interpretability. At least in credit scoring, I don't want to make a general conclusion, but in credit scoring, there is no arbitrage. And one way out of this situation, the low adoption equilibrium, is to promote the use of natively interpretable models in the IRB context. And the key question is whether these methods can reconcile economics and statistical performance. Okay, so in the report, we discuss other challenges posed by ML, the challenges of governance with data management, technological infrastructure, and the training also. The challenge of operational risk, especially with the hyperparameters and overfitting. So even when properly controlled for by cross-validation, random grid search, and so on, setting the hyperparameters values always relies on a set of arbitrary choices left to the judgment of the modeler, and there is an operational risk and specification of question of fairness, and we have also a paper on this question to test the fairness of credit scoring models. Okay, so thank you very much. And sorry for taking a bit longer than expected, but I think that we have time for now a few questions.